These are your notes for section 5.9 on linear programming. Objective and what's the point? Okay, we're going to solve a linear programming problem from scratch, which means it's going to be kind of lengthy. I'm going to tell you these are long problems, okay? We are going to recognize properties of systems of inequalities, and we're going to solve problems using this method of linear programming. There are so many applications here, and I've mentioned this before. Think the business, and I'm going to go through some more examples here. I took a whole class on just linear programming in college. That's how important this type of problem-solving method is, and we're going to get a little taste of it today. Okay, you remember the Lego from yesterday's notes? Okay, we talked about these tables and chairs. What the table looked like this. This is horribly bad, and then it kept going back like 2 of those, and then the chairs were like, I think, was this right? Are there 2 blocks at the top? I'm going to have to look it up in the picture now. Or 1 block at the top. Legos, where are you? There they go. 1, 1, 1. That's just what it looked like. Okay. Let's pretend like you made furniture and you've had these like gigantic Legos. So like maybe like kids' room furniture or something. I'm talking about, we're really going to make like model chairs, not model, like real chairs that look like Legos. I don't think they'd be very comfortable necessarily, but we're going to actually make these. They're not just Legos, they're like real chairs that people can sit in. Okay? Let's say that Tim is the guy who's going to be making these. He's going to make profit. He's going to make $900 for a table. Okay, that's how much he's going to, maybe not, profit, that's how much. Oh, it does. It says he makes $900 for a table, and he's going to make $600 for a chair. How much should he produce to maximize revenue? Okay, we are going to go to page 355 and 356 in our book, and we are going to look at this together here. Okay, here were the system of constraints that we had before. The 2 blocks for a table plus 1 block for a chair, because if you remember, I only had 12 rectangle blocks, and there are 2 square blocks for a table, 2 square blocks for a chair, and I only had 16 square blocks, and you can't have negative. We just said he makes $900 for each table and $600 for a chair. How many should he make? Because you're going to be limited by how many materials we have. So he needs to figure out what's the best way to make these so that I make the most money. Okay? If I was going to graph the system of equations, the lattice points, and this is what this is telling me here, is going to be our region. The feasible set for Tim's system of inequalities is a set of lattice points in the shaded region of the graph of those systems. It also includes the line for a $3,000 revenue and 5 other revenue lines. And this is what I want to talk to you about. This graph here. Okay, here is our feasible region. Do you see it? It's shaded. Let's talk about how much money we want to make, and I'm going to go here. Let's talk about this. This is a revenue equation. He makes $900 per table plus $600 per chair. And I'm going to say R for revenue. Can he make $8,000? Okay, I'm asking you that. Well, line 1 here is, let's say he wanted to make $8,000 total. He can't make $8,000 if you see here. Because if you graph this line, 900t plus 600c equals 8,000. When you graph it, it is a kind of like beyond our possible combinations we can have. These are our possible combinations because we are limited by supplies. In order to make this, I would have to make more tables and chairs. So I cannot make $8,000. Can I make $7,000? Well, that's the L2 line. This represents that line. Okay. I also cannot make $7,000. You can see it is beyond the region. Okay. Can I make $3,000? Well, I definitely can make $3,000. That's the 6th line. I could do lots of things to make $3,000. Maybe not lots, but let's see. I could make, oh, look, 2 tables and 2 chairs because we're only looking at the lattice points here. And I would make $3,000. But can I make more money than 3,000? Yes, I could make 4,000 because L5 is the 4,000 line. If I make, oh, here it is, 1 table, 5 chairs, it looks like, I would make $4,000. I can't tell. I think that's it. Can I make $5,000? $5,000. Any lattice points here? Maybe right here. I can't quite tell. Oh, or I could just make 8 chairs, no tables. Okay. But this is what the one I'm most concerned with is this $6,000 line, this L3. It's right here. If I make 4 tables, 4 chairs, I should make 6,000, which should be the most money I make. Okay, let's talk about these lines for a second. Why are they all parallel? Well, if I get C by itself in all of these equations, this, what I'm plugging in for revenue, is not going to affect the slope of the line. They're parallel because that rate of change, like I said, let's get C by itself in this first one. Minus 900t, minus 900t. Make this smaller here. 600c equals negative 900t plus r. That revenue is something we're just going to figure out. We're going to plug in. Divide by 600, divide by 600, divide by 600. C equals, this is going to be negative 3 halves t plus whatever the revenue is, divide by 600. The slope is always going to be negative 3 halves. The only thing that this revenue is affecting is the y-intercept. So that makes the line go up or down. If I want more revenue, the line goes up here. And if it is less, I go down. The way linear programming works is they've looked at a whole bunch of these plug-in numbers to figure out revenue, and they realize always the most profit, it was not always at this type of point, it was at one of the boundary points of your region. Because I want you to think about it. If the line was a steeper, not steeper, excuse me, flatter rate of change, where's the ruler? I guess I can't have a ruler here. Well, if it was a flatter rate of change and they were all parallel, it would hit this point first. At the slope it hits this point first. If it was steeper, it could possibly have hit this point first. It will always happen at one of these vertices of the feasible region. And this is what linear programming is. Now, as a result of this, we don't have to graph all of these parallel lines. What you can do instead is you just write an equation, and it looks like there's going to be 3 variables. We'll have that 900t plus 600c equals r. And since we know by these super smart people who have plugged in lots and lots of equations to figure this out, since we know that that maximum value is always going to happen at one of these vertices, we can plug in the 3 vertices, guess and check, and see which one does give us the most revenue. So that's how you solve a linear programming problem, and I think it'll make more sense as we do an example. But it's all about these parallel lines, and you will never have to graph those parallel lines again for this, but that's how it's going to work. Okay, so how many tables and chairs should he make? He should make 4 tables and 4 chairs because that is where it hits, and that will make us how much money? It'll make us 900 times 4, which is 3,600, plus 600 times 4, which is 2,400. It's going to make us $6,000, and that's the most money he could possibly make. Okay, so what is linear programming? It's a type of problem where you're trying to maximize or minimize a quantity based on some limitations or constraints that we have. Okay, so if you have some limitations and you're still trying to maximize something, it's called linear programming. The maximum or minimum will happen at one of the vertices of the feasible region. Here are all the places that use it, some examples. They use it anytime there's going to be some type of competition of price because you're trying to make more money than your competitor. Gasoline companies, they might be maximizing or minimizing how much to store things like, or how much of each type of gasoline to produce or something like that. I don't really know because I'm not in that type of industry. Paper, same thing. What size of paper, how much packaging, all that stuff, appliances, clothing, so on. But because they're limited by time and money and materials. Usually time and money are constraints. Labor, materials are also constraints that will limit your profit. But what is most exciting to me is some of these have 5,000 variables and 10,000 inequalities. Like I said, I took a class in college on this. I never had anything this big, obviously. There are computer programs that you can plug all these things in and they will tell you what to do. But this is the bones behind that. Okay, how are you going to solve these? Well, it's not easy, but it's not hard either, okay? It's very systematic. You're going to figure out your variables and you're going to write the system of constraints. I think the hardest thing for most kids is to write that system, because after that, you're going to graph it. You're going to graph it. You need to find some intersections points because you're really worried about the vertices. Basically, you're going to look for your x-intercept. You're going to look for your y-intercept of the feasible region, and you're going to look at where the two lines cross. So you're going to look for intersection points. Those are commands you'll be using on your calculator on some of these. After you do that, you're going to actually figure out what am I wanting to maximize or minimize. I'm going to write a formula for that. There may be 3 variables. There will probably be 3 variables. And that's going to be okay, because you're going to be plugging things in and you're looking to make that third variable as large or small as possible. You will then test the vertices in that equation and you'll interpret the results. So let's look at an example. And I'm sorry about the way this is copied. Chris is a stained glass artist. He makes both. This is from that A worksheet, by the way, that I told you that we would do in class. So this is the 5-9A worksheet. You're not going to do it in class. I just put it on this flip chart. Okay, he makes both small circular pieces and large rectangular windows. A small piece costs him $40 for materials and takes him 4 hours to make. A large window costs $60 for materials and takes 12 hours to make. And in 1 week, he plans to work 48 hours and has $360 to spend on materials. So the first thing I'm going to ask you is, what are my constraints? What is limiting me? Okay? And that's very important, not to just jump into writing equations, because otherwise a lot of people are thinking, I need to make a small equation and a rectangle equation. No. Ask, what is limiting me? And what's limiting me here is time and money. Okay, so let's talk about what those time constraints are. For a small piece, let's go ahead and make our variables. We'll do S for small and L for large, since that's what they already used in this piece of graph paper they have here. I'm going to do a cursive L because L's always look like 1s. So time. A small piece takes him 4 hours to make. So 4 for a small plus, you probably want me to use maybe white here. 4 for a small plus how long for the large? It says 12 for a large. And I only have 48 hours to work. So this, when I put them together, has to be less than or equal to 48 hours. Money is also limiting me here. Okay. It takes 40 for a small and 60 for a large, and that has to be less than or equal to $360. Now, there are also 2 other constraints here, and kids always forget these, and if it's a test or quiz, you do need to know this. I can't have negative windows. So S has to be greater than or equal to 0, and L has to be greater than or equal to 0. And they already took that into account for you when they only gave you quadrant 1 of your graph. I'm going to guess that you're going to forget these, and I hate that because you're going to get a point for a quiz or test on those. So make sure you try not to forget these, okay? So that's my system. We are actually going to graph this now. Okay, we're getting large by itself. So I'm going to go down here for some of my work. I'm going to subtract 4s from both sides. So I have 12 large less than equal to negative 4s plus 48. Divide each and every piece by 12 here. Large less than equal to 4 over 12, that's negative 1/3 s plus 4. Okay, y-intercept of 4, so I go up 4, put a dot. Down 1 over 3. Down 1 over 3. Okay, so there is my graph. I need to find the line. Okay. Next one, I'll try to do over here if I have room. I'm going to subtract 40s from both sides. So I have 60 large less than or equal to negative 40s plus 360. Divide everybody by 60. This works out a lot nicer than I thought. Large less than or equal to negative 2/3 s plus 6. So I'm going to go up 6, put a dot, down 2 over 3, down 2 over 3. And that's nice when you can see where they cross. Down 2 over 3. Here. They're both shaded below, so here is my feasible region. Now, we're worried about where those vertices are. So here's one. That's at 0, 4. This one was at 6, 2. And this one's at 9, 0. Now, there's also one at 0, 0. That one's usually only used on minimizing problems, and it's kind of a duh type moment. So a lot of times I don't write that down. But when it asks for the coordinates of each vertex of the feasible region, we do need to write those 4 down. So I'm going to write 0, 4, 6, 2. Is that 9, 0 we said? And 0, 0. Okay? Here's the profit. We're going to talk about profit for a minute. Chris makes a profit of 120 for a small piece and 340 for a larger piece. So he makes a lot more money for the larger piece, but it takes him a lot more time. So that's one of the reasons we're trying to figure out what works best here. Find his profit at each vertex of the feasible region. Well, first, let's write the profit equation or formula, if you will. So he's trying to make money. So profit equals, what does the profit equal? Well, it equals 120 for a small piece plus 340 for a large. So that's what they were graphing before. So if they were going to graph these, they'd have the same slope, they'd be parallel. We're trying to figure out which vertex is going to touch. Is it a flat line? Is it going to touch this one? Is it a steep line going to touch here? Or is it kind of in the middle and touches 6, 2? So we're going to plug these in and see what works. And remember, this is SL is the way these ordered pairs are going. So plug in 4 for large, and I'm going to get, let's try 0, 4 first. If I plug 0, 4 in, what do I get? Nothing for the small, and I get 340 times 4 for the large. And that gives me $1,360. Plug in 6, 2, and what do I get? 120 times 6 is 720 plus 340 times 2, 680. 1,400, so I do make a little bit more money this way. And what else did I need to try? 0, 0, I'm obviously going to make no money. And what if I have 9, 0? Then I'm just going to make 120 times 9. And I get 1,080. So how many of each side should he make? Well, he wants to make $1,400, so he needs to make 6 small windows. And he makes 2 large. Okay, all of the problems, yes, are going to take this long. But I don't think I give you that many. But this is the process we're going to do. Okay, we did it. That's it. And I will talk to you later.